Good morning, everybody. I would like to say welcome to the very last chapter. I said that. It's the very last chapter. Man, sun is out. It's 1,000,000 degrees. The end of the year is upon us, and we are going to dig into nuclear chemistry. So the thing is with nuclear chemistry is it's really weird, man. It's like a part of chemistry that probably shouldn't even be in chemistry. It's more like nuclear physics. Like it's all like math and stuff, not a whole lot of chemistry. You can't really take nuclear stuff, put in a beaker, and watch a chemical reaction happen, because it's not a chemical reaction. It is a nuclear reaction. So this whole time I've been telling you, like, inside the nucleus, it's like that's it, right? Oxygen is oxygen. There's like this many protons, this many neutrons, and that's that. Well, I kind of lied. Stuff happens in the nucleus. And that's what we call nuclear chemistry. It is literally where the nucleus, for whatever reason, and we're going to learn, well, for us, we're going to learn like the two major reasons. The nucleus becomes unstable and it literally breaks apart, right? And then you have what we call a nuclear change, where something like nitrogen can turn into oxygen, where uranium can literally turn into lead. These aren't like kind of changes. It's not like a chemical change, right? Where all the atoms stay the same and they just sort of get like rearranged, right? So you have hydrogen gas and you have oxygen gas, and that makes H2O, water. No, it's not like that. It's literally where carbon, like charcoal, turns into nitrogen. Yeah. But that's what nuclear change is. It's when the nucleus changes and the atom itself, like the element, actually gets converted into something else, which is really trippy. It's also, oh, by the way, where we get all of our energy. So as we move forward in this amazingly wonderful world of ours, with all the most incredible technology that the human race has ever seen, we are in the process of slowly, well, not slowly anymore, actually, big picture, we're like jumping off a cliff, killing ourselves with all this like carbon-based fuel. So there's a lot of people who want to do nuclear energy, right? Because that's the other thing that we get. We get nuclear energy. We get so much energy out of a nucleus. It's what the sun uses, right? It's what a nuclear bomb uses, and it's what nuclear power plants use. And so we're going to look at a little bit, like just a touch in, to see like how that happens. Like, how do we get uranium into electricity? Stuff like that. So the first thing that I would like to do is talk about what makes a nucleus stick together and what makes it unstable, and then we can talk about all the other good stuff. So let's do that right here in nuclear chemistry, last chapter of the year. Yeah. All right. So nuclear chemistry, like I said, it is the chemistry of the nucleus, right? It's changes in the nucleus. And when the nucleus changes, you may end up with a completely different element. Does that make sense? Okay. All right. So, and anytime we talk nuclear chemistry, everyone's like, ooh, radiation and like aliens with like four heads and stuff. But really, radioactivity, this is caused by an unstable nucleus. So when a nucleus becomes unstable, right, it breaks apart and bits come flying out of the nucleus. And the bits that come flying out of the nucleus is this. It's like radioactivity, right? And so let's get an actual definition of radioactivity. It is the spontaneous disintegration of a nucleus through emissions. Hold on, man. Computer's not being nice to me. Through emissions of particles or electromagnetic radiation. So what is radioactivity? It's when the nucleus crumbles and stuff comes flying out. And there are two basic kinds of stuff that come flying out. We get particles, or we have really super high intensity light. It's light that we typically can't see with our eyes, but it's there and it's powerful. Just ask anybody who's been near Chernobyl; they will tell you. So you might be asking yourself, Stu, what's up with the stability of a nucleus? Well, here it is. Oh, let me back down here. But there are two things that can cause an unstable nucleus. The first is more than 82 protons. So this is the magic number, and this is actually lead. Lead is the biggest stable nucleus. Anything with more than 82 protons is going to be unstable. Guaranteed. This is just because nature, right? And the reason being is, if you think about it, protons, right? I'm talking about protons here, right? All protons are positively charged, right? So imagine you have a bunch of magnets and they're all north, so they're all pushing away from each other, and then you have to squeeze them into an unimaginably small place. Eventually, what happens is because you had so much repulsive force that like it literally just explodes itself out. So 82 is the magic number. This is the last element that can be stable. Once you have 83, unstable because of that repulsive force of the protons. Do you guys understand what I'm saying? So this is like one way, too many protons. The other way is, believe it or not, too many neutrons. Even though they're neutral, they can make things a little bit unstable for the exact opposite reason as the protons. All right, so protons are repelling because they're all positive, right? Neutrons, they have absolutely no force whatsoever, so what could possibly be the problem? Well, there's too much of this stuff. There's too much of stuff called the strong force. So here's what happens inside the nucleus. There is a force that exists in nature, and it involves all matter. It's called the strong force. But you and I will never, ever experience it directly. It works very much like gravity, right? You know how gravity keeps us stuck to Earth, right? You throw a brick in here, it's going to land right back on your head because, gravity, like an attractive force. Well, gravity works, and we're used to it, and that makes sense to us. However, the strong force has a range much smaller than gravity. So, for example, when I say range, you need to be in like outer space, like way outer space, really far away from Earth to escape the pull of Earth's gravity, right? It's a huge distance. However, the strong force is an unimaginably small distance. It can barely reach across the nucleus of an atom. So the distance, like its range, is intensely small. Like I said, the size of a nucleus of an atom. Outside the nucleus, the strong force, that it's too far away. There's no attractive force. It's like taking a magnet on the fridge, right? So gravity and magnets have vastly different ranges, right? So gravity of the Earth goes out like forever, but like a magnet, and like a kitchen magnet, the distance is like maybe like this until like there's no more magnetic force. That means like, so the magnet has a very small range. The strong force is even smaller. The thing is though, like scientists are not super always like creative, and they're not trying to be like mysterious when they name things. So like the black hole, they're like, what is it going to look like? Well, we think if you look at it, it'll look like a black spot in the sky. It's a black hole in the sky, so they called it a black hole, right? So the strong force, guess how you would describe the force that holds the nucleus together? And it's freaking strong, man. Hiroshima and Nagasaki kind of strong, because that's what we're talking. That's the kind of force that we're playing with those things. So what happens is these neutrons, and I like to kind of get off on my tangent there. The neutrons have no repulsive force whatsoever, so there's nothing pushing them away. It's only the strong force squeezing them together. So once you have too many neutrons, the strong force becomes overwhelming to the nucleus, and it literally just crumbles it to pieces, and the bits go flying out, and that's your radiation. You get what I'm saying? So let's review right quick. Neutrons add this attractive force that we call the strong force, right? So this attractive force is called the strong force, and it helps to offset the repulsive force of protons. So that is how the nucleus stays together. It was quite a mystery for quite some time. Like, how do positively charged particles stay together? The calculated force of that is like unbelievably huge, amazing amounts of force to keep protons close together. Well, nature took care of that by having a strong force. So that's how they can stick together. Problem is too many, bad things. So the bigger the nucleus, the more neutrons are needed. In other words, the more protons you have, the more neutrons you need, right? Because if you have like 10 protons, there's a lot of like repulsive force. So you have to add in a bunch of like attractive force, strong force. And that happens when you have the neutrons, because that's basically what the neutrons do. They like add strong force. However, too many make the nucleus unstable, because if you can imagine that like implosion force, if it gets out of hand, it's going to crumble, and it's a balance, y'all, right? It's a balance. It's a balance between the repulsive force of the protons and the attractive force of the neutrons from the strong force. If you have too few neutrons, like not enough, like let's say you had 10 protons and 1 neutron, that is not enough strong force, attractive force, to keep that nucleus together, and it's just going to fall apart. However, if you have like 10 protons and 30 neutrons, that thing's going to like collapse in on itself, then just like disintegrate. Got it? So it's a beauty balancing act, right? And the reason why we only see things that exist in that beauty balancing act is because anything outside those edges, the nucleus disintegrates and it's just no longer there. Like nature takes care of itself. You know what I mean? Great. So here we have this thing called the band of stability. Why do we call it the band of stability? Well, there, it's a band, right? Like right there. So it's like if we graphed, and what they did is they graphed the number of neutrons compared to this here is like the number of protons, right? So if it's 1-to-1, it'll be like straight like this, right? This is your 1-to-1 ratio, and this is 1.5 neutrons to every 1 proton, right? So the band of stability tells it that the nuclei need to have a neutron-proton ratio between 1 and 1.5 to be stable. Why? Because nature told us that. You know what I'm saying? Like, but it's not perfect, right? And it's more of like a suggestion. As you come down here where it's really small, it's way more of a 1-to-1. But as you get more and more protons, you need a ratio edging more to having more neutrons. And if you look, there are a few, like see this guy right here, whatever element that is, whatever this one is, there are a few that are outside this band of stability. It's more of like a zone, like a probability. So inside that zone, we're probably going to be nice and stable. Does that make sense to y'all? Great. Oh, by the way, this is how we make some radioactive medicine. Well, how we can tell that it's going to be radioactive. Like if we need to get nitrogen radioactive, nitrogen is sort of down in this area, right? You can like add a whole bunch of neutrons and get it up to here in this area, and then you'll have radioactive nitrogen for whatever reason you might need. Like we use radiation for all kinds of stuff. So yeah, there's a band of stability. Between 1 and 1.5 neutrons to protons, we'll have a relatively stable nuclei, which is great because then it doesn't like crumble and turn into something weird and spit out radiation and burn your face off, which generally ruins people's days, having their face burned off. Typically, not always, I guess. People are into what they're into. So the next question, I'm sure, that is burning inside your brain right now. Dude, Stu, you telling me what makes an unstable nucleus? Too many protons is unstable, too many neutrons is unstable, and then there's that ratio thing where there's like, if there's too many neutrons or too few neutrons compared to the protons, then there's like, okay, so what happens? Nuclear emissions. So again, names, not trying to be difficult. Nuclear, it's coming from the nuclear, and emissions, this means, being spit out. So that means nucleus stuff being spit out. Direct translation, right? But literally, it's where unstable nuclei break apart. And how do they break apart? They spit out particles, and that particle is called radiation. Right? So radiation, particles that come spitting out of a nucleus as it crumbles apart. And so I need you guys to go to table O, because that is where we are going to see the only bits of radiation that we are going to look at. Now, how many kinds of radiation are there? Dude, the imagination is like the limit. Not really. I'm sure there's some natural phenomenon that's the limit. But for right now, let's just say there are like lots and lots of subatomic particles that could be considered radiation. But for us, we're going to do alpha, beta, gamma. And alpha, beta positron, gamma. Okay? So the first one, alpha, let's look at alpha radiation. Alpha radiation is labeled like this. There are two ways to label like symbols. We use this, He42, or this little like Greek Roman numeral A, not a Roman, I don't know what it is, that little Latin, Greek, I don't know, the symbol that they use when they're being all academic and stuff, that little squiggly A. And so an alpha particle is made up of 2 protons and 2 neutrons, and it's where a 2 proton, 2 neutron chunk of the nucleus gets smashed out and goes flying through space. Got it? So, a couple things I wanna like point out here is, just like before, this right here, this corner, this is always going to be mass. And this down here, this bottom corner, we've always had as the atomic number, but we're going to change that up. We're going to refine our definition. Okay? The bottom left corner now is going to be nuclear charge. Look how nice I wrote with my left hand. Okay. So the upper left is mass. So the alpha has 2 protons, 2 neutrons. That's 4 atomic mass units. So I put the number 4 there. And down here in the corner, I have 2 protons, so it's a positive 2 because there's 2 pluses. You dig? Now, how do we know that that alpha radiation is alpha radiation? Well, we put it through a device to measure charge, and it has a charge of positive 2, and we put it through a mass spectrometer and it has a mass of 4. So any particle that comes out of the nucleus with a mass of 4, a charge of plus 2, we call that alpha radiation. That's it. And here, my friends, is what it looks like in a nuclear equation. Much different than a chemical equation. So in a nuclear equation, here we have radium. This is radium-226. And you know why we call it 226? Because isotopes. Remember isotopes. Same element, different number of neutrons. It plays a huge part in nuclear chemistry. So, right down there. I meant down there. This guy. Radium-226. Spontaneously spits out this thing. It turns from radium into radon. And look at the difference. See, our mass went from 226 to 222, and our nuclear charge went from 88 to 86. Well, man, we know that mass and charge don't magically disappear, right? So, what we know is that the total mass that we start with must be equal to the total mass that we finish with. Bam. You dig? Same thing with the nuclear charge. The total nuclear charge that we start with has to be equal to the total nuclear charge that we finish with. And that is what alpha radiation looks like in a nuclear reaction. So one other thing about radiation. Radiation can kind of get through things because it's smaller than a nucleus, right? So if everything is made out of atoms, and atoms are mostly empty space, if you have something smaller than a nucleus, it can go right through things. Which is kind of a problem with radiation, because it goes through things. However, not all radiation is the same, so not all radiation can penetrate through things equally. And alpha radiation is terrible. This stuff, alpha radiation, someone's like, oh, there's alpha radiation. Just chill. The hair on my arm is enough to block radiation. This shirt is enough to block alpha radiation. My skin, the top layer of dead skin cells, is enough to block alpha radiation. Very, very weak radiation. Very weak. Right? So who cares about alpha? Well, a lot of people, like say if somebody has cancer and they need to put radiation into their body to kill cancer, why not alpha? That way, when our little alpha emitters gets absorbed by the cancer, it spits it out and gets absorbed by the cancer cell and can't go through into our body, right? Because if we took radiation that was like unbelievably powerful, like the radiation will go through the cancer, pass right through and not do anything, and then like hit our brain and give us more cancer in our brain or something. So, you know, everyone's like, oh, it's stupid. Well, you know, they're different things for different purposes, you know what I'm saying? So let's go to the next one, beta. All right, so beta, let's look at right here. Let's go to a different color. Let's go to orange. Beta has a mass of 0, so it has no mass, and it has a charge of -1. Well, that's really similar. That's really similar to like an electron, isn't it? Right? -1 charge doesn't weigh 1 atomic mass unit. Basically, so small that we can ignore the mass. And that's basically what it is. It is a high energy. And like when I say high energy electron, dude, I'm talking like triptacular amounts of energy for an electron. And what happens here is a neutron, right? It's neutral, but it's the reason why a neutron is neutral is because it has a protons and neutrons are made out of other things. Yay, physics. So the things that make up a neutron, you have a positive aspect and a negative aspect, and that's why the neutron is neutral, because there's a positive charge and a negative charge inside the nucleus, or inside the neutron. Problem is, too much strong force, the thing is like getting ground to pieces and it breaks. And the negative part goes flying out and it leaves behind a proton. Right? So this is literally a neutron changing into a proton. I know, it's trippy. It's like saying, oh, I have on the counter an apple, and in 2 minutes, the apple shall become a banana. And that is exactly what happens. So it's crazy, man. It's crazy. Anyway, let's look at thorium. Dude, keep your ears out for thorium, y'all. So remember I was talking about nuclear energy, getting rid of the carbon-based fuels? Carbon-based fuels are going to kill us all if we don't do something about it. I know it's all political and blah, 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 whatever. Put all the politics aside, man. Carbon-based fuels need to go because we want to stick around. Nuclear energy is a really great alternative. The only problem is, like, if anything goes wrong with the nuclear power plants as they are designed right now, like, it's uninhabitable for, like, longer than humans have been walking the earth. So you get a little patch of earth where, like, humans can never, ever, 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 ever go, and it statistically happens often enough that it would be hard to be here. But there's this thing called thorium that can be used for nuclear fuel in a relatively safe situation. So check it out. Do your Google search. Anyway, this is what happens when a beta particle comes out. We start with thorium-234 and palladium-234. Oh, okay. And so the total mass stays the same. So the mass of my particle is 0, but look closely here. The total charge on the left must equal the total charge on the right. So if I think it's palladium, man. I'm probably wrong, but that's okay. This element right here, this big giant radioactive element, it has a nuclear charge of 91. So how do you go from 90 to 91? That makes no sense. Well, it happens by spitting out an electron. Do you guys get what I'm saying? Yeah. Okay. They need to charge a computer. Anyway, so there's a beta particle. How do you know it's a beta particle? Because it has a mass of 0 and a charge of -1. Beta particle comes spitting out of the nucleus. Next one, positron. Positron, look at the notation. It is a 0 mass and a +1 charge. Oh. Wait, what? Just like an electron, only positive? Yeah, this is what we call a piece of antimatter. It's like an anti-electron. So what happens is it's antimatter. It's a real thing. All it is matter that is exactly like regular matter, but with an opposite charge. So a positron is like an anti-electron. Yeah, it's real. It happens. It's like actually a real thing. Fun fact, what happens is if a piece of antimatter and its regular matter counterpart, if they collide, they undergo what's called annihilation, and they just explode and they turn it back into energy. Because remember, matter is basically like a condensed form of energy. You can think of it like that. So yeah, they like uncondense and turn into just straight up energy. But anyway, let's go back to positron. Positron is almost exactly like beta, only it's a positive charge that comes whipping out from like the neutron. So this is what it looks like. Potassium-37, yeah, sure enough, potassium-37 is radioactive. You eat too many bananas, you're going to be radioactive. Yeah, radiation isn't necessarily bad. It's all around us. We need radiation to live, actually. Our faces use radiation to make vitamin D from our skin in this general area. It's not all bad, dude. It's just like, movies and the news like to make people freak out because people watch when you freak out. So they like to make radiation up to be this crazy scope. But I mean, you should be like scared of it and like treat it with respect, but it's not always like which is like what Hollywood makes it out to be. Because, yeah, bananas are radioactive. Anyway, the potassium okay. Oh, so the mass stays the same, but look at what happens here. The mass drops by 1, so our positron emission has a charge of +1 and mass of 0. Bam! So let's talk about like the ability to go through things, or the penetrating power. Alpha, it's like the worst. It's like beta radiation, that can get through some stuff. We'll call that medium, because it's all relative, really. So alpha is the worst penetrating power. Beta is like the medium. This is where you need to put on a lead vest, right? Like when you go to the dentist and you get x-rays, they put a lead vest on you or something like that. Lead vest will definitely block beta rays. You'll need some serious like barrier for beta and positron radiation. Again, is it all bad? I don't know, man. They use positron emission to like image medical stuff, so it can't be that bad. I've had a million x-rays and it's kept me alive. I'll take that. So good or bad, I don't know. You tell me. Last one, gamma. Here's the deal with gamma radiation. It's this thing, this like upside down fish. Again, I think it's Greek alphabet or whatever. Gamma radiation is high energy electromagnetic radiation. It's high energy light. And when I say high energy light, I mean gamma radiation is typically pretty bad. It's typically really bad. Like this is the stuff that has the potential to have enough energy to be what we call ionizing radiation. And when radiation has the label ionizing, that's the kind of radiation that everybody's talking about for danger, because that has plenty of energy. If it does collide with your atoms and molecules, it can shred them. Like that energy can be absorbed by the molecules. It's too much, and they just like explode apart. It's like a grenade for your molecules, which one zap at a time, yeah, who cares? You can lose a molecule or two. When it happens a lot, what'll happen is you'll have tissue damage. It's literally like getting burned. So like if you see Chernobyl or like all these other things about like people getting like radiation burns, like if you ever seen the horrific video of what happened to people in Japan after the bombs were dropped, like blisters and all kinds of horrible stuff, that was from a waft of radiation that went over them after the blast. And there was so much radiation that so many molecules were broken apart. It was just like they got burned, because that's what burning is. It uses heat to shake your molecules until they break apart. Too much radiation all at once does that. It like breaks down your tissue. And what we have been accustomed to learning is that it gives you cancer, but that's only if you get enough ionizing radiation to cause damage to the nucleus in a way that mutates it. So not highly likely, but likely. But like it happens, you know what I mean? So you need a lot of radiation, which means if you go out in the sun and you get a sunburn, it's not a guarantee that you're going to get skin cancer. All it does is it increases the statistical probability that some kind of cancer will develop. Because every time you get hit by radiation, it's a roll of the dice. Is this going to kill the cell, or will it cause like some kind of weird mutation? Guys, get what I'm saying? Awesome. So gamma radiation, it's just high energy light, but man, is it high energy. And this stuff goes through anything, man. This stuff is crazy. It can go through Earth, like through Earth. Yeah. Yeah. And so it goes alpha, beta, positron, gamma. So gamma radiation goes through just about anything. Got it? And yeah, again, this is not stuff to remember. Table O. Go to Table O, and it's got everything you'll need to know. Table O has got everything you need to know. All right, so let's rip through this very quick. Alpha, mass. What is that? Well, if you go to Table O, it's right there. It has a mass of 4. It has a charge of 2. And the symbol, like what you'll see in an equation, looks like this. They use He for 2. Now, why He? Because it's a helium nucleus. You guys get what I'm saying? It's like helium has a mass of 4 and a nuclear charge of 2. And at first they're like, dude, I think it's helium. But then there were no electrons, so yeah, that's just what it was. All right, so beta and positron. Remember, these guys have no mass, right? The particles are too small to have mass that we would even consider. Now, beta, I can't remember the charge, but a positron. Positron? Yeah. Okay, that helps me remember what the charge of a beta is. And so, wait, what were these? Oh, man, I can't remember. Oh, wait. Little squiggly B. So, I'm going to use the squiggly B. It's going to go like this. 0. This is going to be a -1, and this is going to have the same symbol, but a 0 and a +1. Why does it have the same symbol? Remember, these two things are like complementary pieces of matter. The beta is a piece of matter, and the positron is its corresponding antimatter. So they have the same symbol because they're the exact same thing except for their charge. And the penetrating power, medium. We'll get through some stuff, not all of it. And gamma, mass of 0, charge of 0. This one is the upside down fish, 0, 0, and it is very high penetrating power. You can go through anything. Like, put on your lead vest, ain't gonna stop you. Nope. Yeah. So, is that it? No! I bet not. Oh no! Dang it! You thought we were done, didn't you? Man, not yet, because we're gonna talk about this, well, that thing. Transmutation. Now, transmutation, remember, scientists come up with names. They're actually trying. Science is hard enough. We don't need to make funny names like artists who come up with mauve. How am I supposed to know what mauve is? What is that? Like, mauve. Like, okay, orange. I know what orange is. It's the color of an orange, but mauve. Weird. But transmutation isn't weird. Man, the definition of transmutation is like right there in the transmutational name. So to transform is to change, and to mutate. What does it mean to mutate? You get the idea? Something's changing here. So transmutation is when the nucleus of one element changes to the nucleus of a different element. We need gold sparkles for this one, man. It is a different element. Like completely. This is where it's not lead doesn't turn to gold, but gold will turn to lead, and it's like that drastic of a change. Like in carbon dating, like when things die and like just don't decay right away, they're carbon-14, an isotope of carbon with a mass of 14, slowly transmutates into nitrogen gas. So you can literally get a charcoal, a big lump of carbon-14 that looks like, for all intents and purposes, like a lump of Kingston charcoal, and over maybe 10, 20, 30 million years, it'll evaporate into nitrogen. Crazy, man, but yeah, there it is. All right, so table N. Table N is going to tell us how stuff transmutates, okay? So, carbon-14, man, it's almost as if I knew this was coming. This is a really popular one. This is how we tell how old dead organic matter is. Not fossils, because fossils are where all the organic matter is gone and it's been replaced by minerals. But, like, let's say we found a skeleton in a cave, or like the Iceman. You guys remember the Iceman that we found up in the mountains because all the glaciers are melting? Because remember the whole carbon-based fuel thing that I'm talking about, as we are slowly killing ourselves, like every other civilization in human history has ever done. Like as the glaciers are melting, it revealed this like dead guy from like who knows how long ago. Well, when he stopped eating, he exited the carbon cycle, and so all of his carbon started to decay. And this is how they dated or tried to see how old it was. So what this means is that it will take 5,715 years for half of the carbon-14 to go away. And how does it do it? Like, what happens? Right here. For transmutation, this is what we're looking for. This tells us what kind of radiation comes out of the nucleus. And it's not like, well, on occasion, it's like every time. Why? Because nature. So every time an atom of carbon-14, remember carbon, 6 protons, 14, so it's got what? 12, it's got 8 neutrons. Every time that thing undergoes transmutation, it's going to spit out this thing, a beta. You guys got what I'm saying? That's how you know. How do we know? Because we have done this like 1,000 majillion times. We've been looking at stuff forever. It's not like we're guessing at this anymore. So, 2 kinds of transmutation. One is called natural transmutation. And natural transmutation, this is what you're going to get in table N, right? This is natural transmutation. This is what happens naturally, just all on its own. We don't need to do anything to make natural transmutation happen. So, what is natural transmutation? It is one element decays into a new element and an emission. So, how does it decay? Yeah, it spits it out. So, carbon-14 transmutates into a beta particle and a new thing, which I think is nitrogen, I've been saying, right? So how do you tell? Dude, it's got one reactant. There's one thing. That's it. Oh, yeah, nuclear decay. This is another term for natural transmutation because it's when the nucleus decays or like breaks down over time, which is what decay means. And so here's what it looks like. You start with one element and you end with a brand new element and some kind of radiation. And what we're going to see is like something like this. Like just blank, blank. So here we have francium-220. It's 87. It spits out an alpha. What does francium turn into when it undergoes alpha decay? That's the question. What does francium transmutate into when it undergoes alpha decay? Well, let's check it out. We know that the total mass has to add up to 220. So this is going to be 116. This will be 116. That's what the mass is going to be. And then this is 87, and this is 2. 2 plus what is 87? Hey, why? Oh, he's got his headphones on. Nice. Shoot. I don't have my reference tables with me because I have no idea what that here. Wait a second. Okay, here we go. 87, 87, 82. Oh, so right there, 82, that's where lead ends, so that's my last stable thing. Bismuth, radioactive, polonium. Oh, shoot. What number did I need? Guys, come on, man. You asked me to use my brain. Oh, 85. So what element has 85? Astatine. Nice. Okay, so this turns into astatine. Easy. I can do this. So can you. It's not that hard. You have to add and subtract, guys. Adding and subtracting. Oh, and then you got to look it up on the periodic table because who would memorize this stuff? Like, don't memorize it. That's stupid. God, please memorize things. Okay, so here we have iodine 131, very often used for thyroid things because your thyroid, it's a gland right here, and every single one of you knows at least minimum one person with a thyroid problem. Everything your thyroids just don't like to work. So what they do to see if your thyroid works is they'll make you drink some iodine, then you take a picture of your thyroid. And if you have hypothyroidism, in other words, it's like working too hard and going too fast, it'll glow. Like a little too bright, right? They calibrate it with like thousands of people. But if you have hypothyroidism, it means it's too slow. It won't glow enough because your thyroid gland absorbs iodine like crazy. And iodine 131 is radioactive. So let's check it out. 131 here, 131 here. So my mass is going to be 0. I've got 53 here and 54 here. So wait, 53. 54, 54, and what is 50? Okay, so that's going to be a -1. Okay, that's going to be a beta particle. And I'm going to wait for a minute to see if you can see the problem there. Because everybody does this. I did this on purpose because every year, everybody does this. And there is a final coming up, so why not learn it now? Yeah. Do you see how iodine has a nuclear charge of 53? Can iodine have a charge of 54? Man, no, don't be silly. Anything with a 54 charge must be selenium, Se, right there. Okay, so we have to change that, guys. Se. There. Better. If the nuclear if this number if the atomic number, not the nuclear number, if the atomic number, if that number right there changes, guys, it's going to be a new element, right? Because the protons identify it, blah, blah, blah. Okay, all right. Oh, hey, potassium. Remember, radioactive potassium. Oh, it's going to get you. Okay, what if it just gives you like this? How are you supposed to know? I didn't teach you. Nobody taught you that. How are you supposed to memorize what potassium... Dude, stop being a knucklehead and just look it up. Oh, wait, not there. Let's come over here. I think it's table O. Oh, there, no. Oh, table N. Right there. Give me a sec. Let me see what I can do here. Let's go back to the up and down. Okay, so it said, oh, potassium. Okay, here I have potassium, 37 and 42. I'm too knuckle brain to remember. Okay, 37. So potassium, 37, right? Ah, that looks like a positron. See how it's like the funny B thing with a plus? So that's going to be a positron. So I'm going to come back here, and I'm just going to throw that right here. Positron has a mass of 0, a charge of +1. This is going to be easy. So, mass of 37. 0 plus what is 37? This is not mathematically difficult. This is +1, so x plus 1 equals 19. See, because my total is 19. So here, these two numbers have to add up to 19 in all. So it's going to be 18. What element has 18 protons? Oh, I just missed it. Oh, argon. So potassium, that's radioactive in a banana, will slowly degrade into argon gas and float up out of the banana. I have a feeling it'll be turned into banana bread way before that happens. All right, coming up to the end here, guys. Artificial transmutation. This is human-made transmutation. We basically take an element and we smash it with neutrons. That's it. This sort of setup exists in any hospital that does radiation because the stuff degrades so fast. You have to make it on site before you pump it into the people because it goes away really fast because you don't want it floating around in them for too long, right? Same exact idea here when you look at the equations. The difference is, you see here I have two reactants. This is what's clutch, 2 reactants, nuclear reactants. And in this case, we have helium, we have nitrogen. It spits out a hydrogen or like, I don't know what that is. Yeah, looks like a proton comes flying out. But the total mass here is 14, and there's 4, so this adds up to 18. So this mass here has to be, there's 1 plus what? Yep, so I have a mass of 17. Here I have 7, and here I have 2, so that's going to be nuclear charge of 9. So here's 1 and 8 equals 9. So there's oxygen. Makes radioactive oxygen. There you go. This one, aluminum. Let's just, I like to do the mass first and then the charge after. So this is artificial transmutation because we're smashing aluminum with helium. 27 plus 4, 7, 8, 9, 30, 31. That's the total mass of 31. I have 1 here, so this is going to be a mass of 30, right? Because 30 and 1 equals 31. I have 13 and 2, that's 15. 15, and then, of course, we got to come here, come down here. Can't handle it looking like that, so I'm going to rotate it clockwise. Who's 15? 15, phosphorus. Easy. Radioactive phosphorus. We use that for tracing and stuff. Cobalt plus a neutron. Still cobalt. We make people drink that stuff. Ooh, uranium-238. Gonna add these two masses. Still stays 92. Still stays uranium. Guess how that works? That's not crazy. That's not crazy difficult. Thank God it's over. Oh my God. Oh, could you imagine if I was gonna go on anymore? It's terrible. 2 things. What is radioactivity? Writing nuclear equations. Do them. Learn them. If you have questions, email me. Or pop a question in the classroom boopity boop thing. Or ask a friend. Or ask Google. They're all very smart. I hope you guys have a great day. It's beautiful outside. Have fun.